All right, so I have some MATLAB code to compute the molar volume of a fluid using van der Waals, SRK, and Peng-Robinson equation of state. And I just wanted to give you an example of how to run them or how to use them. And so how I'll demonstrate is looking at example 2.1 in the text. So in example 2.1 in the text, they ask us to use the van der Waals and SRK and Peng-Robinson equation of state to determine the molar volume of the saturated phases of ethylene at 260 Kelvin. And we're told that the saturation pressure is 30.35 bars. And we could compare to the tabulated values given here. We're given with the critical temperature, pressure, and eccentric factor. And if you didn't have those, you could look those up in the back of the book. So you know Tc, Pc, and omega, and we're given the temperature and pressure at which we'd like to calculate the molar volumes. Okay, so I'm going to slide over to MATLAB. Okay, and so the files of interest is I have a function v underscore van der Waals that'll return the molar volume of a fluid using van der Waals equation of state, and the molar volume will be in units of centimeters cubed per mole. So the necessary inputs are temperature, pressure in bars, critical temperature, and critical pressure, also in bars. It'll return the molar volume in centimeters cubed per mole, and then optionally it'll return the compressibility and ideal gas molar volume. SRK is similar. Okay, so it has an input, or it also has an input of omega, the eccentric factor, similar output, and then Peng-Robinson is essentially the same thing. Could have combined them all in one function, but I kept them separate to try and make it easy, as this is a MATLAB class. Okay, and then also online I have an example script for solving 211. So remember, a script is essentially just a series of commands I could execute in the command window, but this facilitates sharing an example with you. And you could edit and tweak this based on a given problem and update it and solve for your particular case. Okay, so first thing I did is I assigned to variables the critical temperature in Kelvin, critical pressure, and eccentric factor that were provided in the problem statement. If this were a different problem, you could go to the back of the book and look them up. Then I stored the temperature and pressure in bars, both to variables. Okay, and so these were provided in the problem statement. And then I call our functions as such. Okay, so in all cases, I'll return molar volume. And so if I get more than one real root for z, it'll return all of the real molar volumes as a vector. If there's only one real root, it'll just return the 1. Okay. But in all cases, it'll return the molar volume, and then there's additional optional output variables of compressibility and ideal gas molar volume. We're going to get them all here just so we can see for comparison. And so I would call it as, there's my function name, and then there's all the inputs required to get it to run. Okay, and so hopefully this is enough that you could update and tweak this for a particular problem. Okay, and so if I were to run this, okay, I would just type example 2.1 in this case in the command window and run it. And what's displayed and then also just stored in my workspace is here's my molar volume computed using van der Waals equation of state. Okay, and so my code is set up so it'll return all of the real z's and all of the real molar volumes. If there's an imaginary z, it'll get thrown out. Okay, then it's up to you to identify which molar volumes you need. Okay, and so these v's are in the same order as these z's, right? In this case, from lowest to highest. So this would correspond to a molar volume of my vapor, and this would correspond to molar volume of my liquid. And these values agree perfectly with the results given in the text, right? But I have it set up so I return molar volume, z's, and then v ideal gas. So this would be liquid, and this would be vapor. So then after that, I see SRK. So SRK also returns 3 real roots. Here's my molar volume of vapor and of liquid estimated using SRK along with the values of z. And then last but not least, Peng-Robinson. Okay, so molar volume of my vapor, molar volume of my liquid. Again, it returns 3 real roots. In all cases, molar volume of ideal gas is the same for all of them. Okay, cool. So I mentioned Z and V are optional. And just to give you an example, if I clear my screen and go back to my script, okay. So if I were, say, just to type V van der Waals, just to type V SRK, and just V Peng Robinson, okay. Save and then run again. Okay, this time it just shows me the volumes, right? So the return of Z and V ideal gas are completely optional. If my temperature and pressure were different, so that I only had a single real root, so I don't know, let's just see, I haven't tried this, but if I make this, say, 320 Kelvin, and I rerun it, right, in that case I just get a single molar volume, because my code is set up so that it only returns real roots. Okay, so at 320, so if 260, so if I'm at a pressure of 30.35 bars and 260 Kelvin, I'm at saturation. I've moved myself further into the superheated region, and as I get further away from the saturation curve, I only have one real root as compared to two. Right, so the multiple real roots is going to occur when I'm on my saturation curve or near my saturation curve. As I get further away, that shouldn't be the case. Okay, and so here's an example where there would have been two imaginary roots, and the code is set up just to return only the real roots. Okay, and so hopefully that gives you enough sense of how to use this. I'll put this example script and these functions on the Canvas page. If you want to use them, just make sure that those functions are in the directory where you're trying to solve problems, so you can point to them and call to them, and you should be all set. And hopefully that helps you, focus more so on solving the problems. And if you want to get an idea for how the code works, you can look at the individual code. And if you're taking my 324 class, we solved the Peng Robinson case in chapter 7 there.